Good evening, everyone. This is photoelectric effect. We have jumped on to modern physics. And how we have jumped on to modern physics is because up till now, till the previous class, we were studying something known as the wave nature of light. We had seen that light has got dual nature. Sometimes it behaves as a particle, and in some cases it behaves like a wave. There are certain phenomena that can be explained with both wave and particle nature, reflection and refraction. So we started with reflection and refraction. Reflection and refraction can be explained both as we consider wave as a particle. Light as a particle. We can understand reflection, refraction, or we take light as a wave. Then also we can understand reflection and refraction. But then there were certain phenomena which can only be understood by the concept of wave nature of light, interference, superposition of waves, interference, diffraction, polarization, three different phenomena. There is one phenomena particularly which cannot be explained by the wave nature of light, and that is the photoelectric effect. Photoelectric effect. Now, for going on to the photoelectric effect, we must understand how this came into being. So this was actually suggested by Hertz. This phenomena was given by Hertz. He discovered this phenomena in the year 1887. Hertz discovered this phenomena, and then we came up with this quantum theory of light. We came up with this quantum theory of light, which tries to explain what is actually happening here. Now, what do you mean by this quantum theory of light? It was proposed by Einstein. And what does this quantum theory of light say? It says that light is not a wave. It basically consists of small packets. Packet like this jar. Light comes in packets, like a packet of biscuit. Every packet of biscuit has some number of biscuits, or light is like a biscuit. It comes in packet. It's the particle. You can count the number of particles. That one packet of light, the smallest packet of light. Right now, the smallest amount of money that you can give to anyone is 1 rupee. Probably you cannot give 50 paisa because 50 paisa no longer exists. So let us say 1 rupee is the smallest packet of money that we have. If you go out and you ask someone, give me an apple, give me apples, he will give you 1 apple. He cannot give you a half apple cut. So 1 apple is the smallest packet of apple that you can get. If you go out and you say that, you know, I only need 1 biscuit, no one is going to give you 1 biscuit. They are going to give you a packet of biscuit. The smallest packet of light, right, comes in packets. They are particles. It comes in packets. The smallest packet of light is known as, the smallest packet of light is known as, the smallest packet of light is known as a photon. So light propagates in packets. Light propagates in packets. It's a particle. That is Planck's quantum theory. Light propagates in small packets or bundles. The smallest packet or bundle is known as a photon. Smallest packet or the bundle is known as a photon. When we talk about photon, then light has got energy. What is the energy of a photon? How much is the energy of a photon? So we must remember energy of photon. Why my voice is echoing? The energy of a photon is given by HF. H into F. H, the new thing that comes right now, this H is known as the Planck's constant. This is also Planck's quantum theory. Planck gave it. Einstein tried to explain it. in more details. Since it is Planck's constant theory, so it is known as the Planck's constant. Have you heard about Planck's constant? This is the first day probably you are hearing it, no problem. This is the Planck's constant. Planck's constant.
6.6 into 10 to the power of minus 34.
6.6 into 10 raised to the power minus 34. What is the unit?
Joule, sir.
Not joules, it is joule second. This is joule second. Planck's constant theory, and a lot of questions have been asked on this H. Basically, in units and dimension, I have seen a lot of questions coming in the previous year where they make H, the Planck's constant, as one of the fundamental units. H, G, and E, they make units like this. So remember, Planck's constant is energy per unit frequency or energy multiplied by time. Okay, HF. F, what is F here? F is the frequency. F is the frequency of this photon. This photon has a frequency. F stands for the frequency of this photon. So this is one way of writing this energy. I can write energy is equal to HF, or I can write F as C by lambda. So the formula becomes HC by lambda. So these are the two formulae that you must remember for the energy of a photon. This chapter only consists of simple things. Remember simple things. You will do very nicely in this particular chapter. Energy is HC by lambda or H into F. Now this energy, which you find out from this formula, put the value of Planck constant. C is the speed of light, 3 into 10 raised to the power 8 meter per second. Lambda is the wavelength, is normally an Armstrong unit, 10 raised to the power minus 10. You will get the answer of energy in joules. But see, the energy of a photon is very less compared to a joule. So it's better to find out this energy in terms of electron volts. Have you known? Do you know electron volts? Electron volt, have you heard about electron volt?
Yes, sir.
1 electron volt. What is the equivalence of 1 electron volt? How much is 1 electron volt?
1.6 into 10 to the power minus 19 joule per second.
Not joule per second, minus 19 joule. So basically, when you find out energy from HC by lambda, that formula, you will always get the answer in joules. You have to put, and then it becomes a very tedious calculation. 6.6 into 10 to the power minus 24 multiplied by 3 into 10 to the power 8. We have a shortcut for this, because most of the time what we are going to do is going to find out the value of this energy in electron volts, because in this chapter, wherever you see energy, it will most probably in electron volt. So you can have this shortcut formula, and the shortcut formula sometimes is written as 12,375. This is approximately same, divided by lambda in Armstrong unit, or you can also sometimes write it as 12,400 divided by lambda in Armstrong unit, and the answer that you will get would be in electron volt. So remember this shortcut, H into C. The shortcut for H into C becomes 12,400, and if you divide it by the wavelength in Armstrong unit, you will get the answer in electron volt. Normally, whenever a photon is given, normally the wavelength of the photon is given in Armstrong units. So from there you can find out the energy of the photon. Do we understand this?
Yes, sir.
Let me see if I can find a formula, where you can just use this energy. I can't, so I'll make a question so that you understand how can you use this formula. Have you noted this down, everyone?
Yes, sir.
So you can write this question here. Question number 1. A photon has a wavelength lambda which is 24,2480 Armstrong unit. Find the energy of that photon. So what you got to do is just to make you understand that if you have this, obviously you will not get a question where they straight away ask you the energy of a photon. And finding out the energy of photon may be one of the many steps that you have to do in the problem. This is just to make you understand that how you are going to find out the energy of a photon. So you can straight away use the formula E is equal to 12,400 divided by lambda and put the value of lambda in Armstrong unit and you will get your answer. I hope you understand what you got to do here. So what will be the energy here? 12,400 divided by 2480. 10 goes away. I think you can divide it by 2 though. It will be 5 electron volts. Yes or no?
Yes, sir.
So this is how you can use the shortcut formula that I have given. The simple one. No one is going to ask you this question, but you will have to find out energy of this energy of photon in many cases. So you can use this formula. Everyone has noted this down?
Yes, sir.
That takes us to the next concept, and all these things are potential questions in themselves. The next concept B, when you're talking about photon, what is the momentum of a photon? Whenever we talk about a photon, we might talk about the momentum of a photon.
H mu by C.
How do you find out the momentum of photon? Okay, it seems like you have prepared this. Well done. So to find out the momentum of photon, we must multiply the mass of the photon with C. M into C. That will be the momentum of the photon, P. And how will you find out the momentum of the photon? Now remember, every photon has an energy. That is hc by lambda. How do you find out the mass of a photon? Remember, this energy of the photon is also equal to mc square, where m is the mass and c is the speed of light. Now combining these three equations, you can find out a variety of things. For example, you can find out the momentum of a photon. Let us first concentrate on the momentum of the photon. What all formula that you can make for the momentum of the photon? The more the number of formulas that you can make, the better you are going to be. So what is the first formula that you can make for the momentum of the photon? P, momentum of the photon. I think I can make the first formula as E divided by C, yes or no? Yes?
Yes, sir.
Yes, sir.
Then I can write E as HF by C, or I can write F by C as 1 by lambda, H by lambda. These are the three different ways of writing the same thing. Sometimes formula number 1 may help you, sometimes formula number 2 will help you, sometimes formula number 3 will help you. The more the number of ways that you can remember, the better you are going to be. Momentum of the photon. Whenever we talk about photons, we might either talk about number 1, the energy of the photon, or number 2, the momentum of the photon. But why we do not talk about the mass of the photon? You hardly see any question where you talk about the mass of the photon. Now, when you talk about the mass of the photon, if you talk about the mass of the photon, have you noted this down, momentum of the photon?
Yes, sir.
Okay. Now, why we don't talk about the mass of the photon? Because the first thing that you have to remember is rest mass. Rest mass of photon is 0. Now, what do you mean by rest mass? Remember, photon does not exist when it is at rest. Photon only exists when it is moving, and every photon is moving with the speed of light. Photon does not exist when it is at rest. Do we understand this? That is why the rest mass of the photon is 0. But when it is moving, it has a momentum. And from that momentum, you can calculate its rest mass. I've already given you the 3 equations. From those 3 equations, since you know that is momentum, you can divide it by c, and you will end up with your mass of the photon. The mass of the photon, and let me just divide all the 3 equations here in yellow. If you divide all these 3 equations by c, you will end up with the mass of a photon if you ever need to find it out. So it will be equal to E by c square, hf by c square, or you can write it as h by c lambda. Do we understand this? Yes or no? These are some small things that are going to come at various parts. They are obviously not going to ask what is the rest mass of the photon or what is the mass of a photon, but we will be using these small shortcuts, small formulae at various stages in solving a question. So there you should be able to remember that we have already done this before. Do we understand this?
Yes, sir.
Okay. Have you noted this down?
Yes, sir.
Everyone in the class, boys?
Yes, sir.
Okay. Now, sometimes we are supposed to find out the number of photons. So we can write this as number of photons falling on a body, or number of photons that are emitted by a body. How do you find the number of photons? So it's very simple. It's simple maths to find out the number of photons. If I call it n, the number of photons which are emitted or falling will be the total energy which is falling divided by the energy of one photon. Do we understand this? If you know what is the total energy falling, you just divide it by the energy of one photon and you will get your answer for the number of photons. So number of photons is equal to total energy. How should I write it? Total energy. Let me write it as U. Total energy is U divided by E, because I'm using E for energy of a photon. Therefore, U divided by E. Everyone understands this? Yes or no?
Yes, sir.
So you can write it like this. Total energy is U. E can be written as H into F if you want to write it, or you can write it as U into H. C by lambda. C comes here, lambda goes here. So you can write it like this. This is the way you can find out, bacha, the total number of photons which are falling on a body, or the total number of photons which are ejected by a body, because we will need to find this out in some question or the other. Number of photons emitted or ejected per second. Now, many a time, instead of finding the number of photons which are falling on a body, they might ask you what are the number of photons falling per second. How do you find it out? Number of photons per second. So let me call it ns. So S standing for per second. That will be equal to total energy divided by total time. So I can write it as power, or let me not write it as total power because that might confuse you. Power falling divided by energy of one photon. Do we understand this? What is the power? Power of the source or power of something which is receiving the photons. So now I can make the formula for this also, beta. Number of photons falling 1 second is P divided by E, P divided by HF, or you can write it as PC. Oops. You can write it as P into C divided by H into F, H into lambda.
HC, sir. Sir,
Yes, beta.
lambda by HC.
Oh, I've written it ulta. Now I think it's correct. Let me know once you have noted it down.
Completed, sir.
Everyone done this?
Yes, sir.
Shall I move ahead? Okay.
Yes, sir.
Now, many a times we have come across this in wave optics also, we had come across a term which was intensity of light. Let us now clarify this term, intensity of light, because these are the terms that are going to come in this chapter. And if you don't understand these terms, it becomes very difficult to understand this chapter. Intensity of light. Anyone has any idea what do you mean by intensity of light?
P by A, sir.
What is P? What is A? What is P? What is A? That's nice that you have prepared it. I am very surprised. Try to understand the concept. It is the energy falling or crossing, energy falling or crossing or emitted, because energy may be falling on it and energy may be crossing a particular area, energy may be emitted by a particular body. All these three things are possible. Energy can fall, energy can be emitted, and energy can be transmitted, energy can be reflected. So energy falling on a body per unit area per unit time perpendicular to the area. How much energy is falling or emitted or transmitted or reflected per unit area per unit time perpendicular to it. Now, what do you mean by perpendicular? If I draw a small area, I hope you can see this small area. Now, this small area, let me draw it in a different way. This is a small area, and I hope you understand this is the area vector. Everyone understand this is the area vector? Area is treated as a vector quantity. Yes or no?
Yes, sir.
The direction of area vector is perpendicular to the area. Now, if this is a small area, how much energy per unit area is falling either in this direction or it is falling in this direction? If it is falling in this direction, it is getting probably absorbed. It is falling. If If it is in the right direction, it is probably be getting emitted or getting transmitted. Do we understand this? So energy falling per unit area, per unit time, perpendicular to the area is known as your intensity. Do we understand this? Yes or no? No, yes.
Yes, sir.
Okay. Please note it down.
Completed, sir.
Okay. Now you can devise a small formula for this. Intensity is I, is the energy falling per unit area per unit time. U is energy. Energy per unit time is power. So you can write it as P divided by E. That is the formula that you were talking about. P divided by E. Power divided by E. We understand this? Yes or no?
Yes, sir.
Okay. This is intensity. Now, as soon as we talk about intensity, there is a small thing that comes sometimes. There may be a problem on that thing. So you can take it as an important note. If you have a point source of light, understand the meaning of point source? If you have a point source of light, and this point source of light has a power P, point source of light having power P, and if you are, let us say, at a distance A, you are at a point A at a distance R from this point source, P is a point source of light, and you are at a point A at a distance R from this point source. I told you about the type of wavefronts that this point source emit. Can you tell me what type of wavefront a point source emit?
Spherical, sir.
Spherical. Well done. It emits spherical because it emits in all directions. Now, if it is emitting a power P, what is the intensity? When I say intensity, I mean how much energy it is, how much energy this point A is receiving per unit area per unit time. So remember the concept, remember the formula. The intensity at point A will be power divided by 4 pi r square. Power divided by 4 pi r square, or I can say intensity will be inversely proportional to r square. Do we understand this?
Yes, sir.
Now, we can now think it of in a different way. Suppose now I have a small area, this point, instead of this being a point, let me make this as a small area. The small area, let us say, of this place is S. Okay, and this point source is emitting, it is emitting light, it is emitting light of frequency F. It is emitting light of frequency f. Now I ask you, how many number one photons are emitted per second by point P? And number two, how many photons are received per second by the point A? A is at a distance of R. I've seen this question come many times in many exams. And students get confused. What is happening here? Now you have this entire thing. Let us find out. If you can tell me what is the answer. Remember, what things are known? P, the power is known. F, the frequency is known. R, the distance is known. And S, the area of this thing is known. From this, you have to calculate what is being asked. I'll give you 2 minutes to solve this.
Sir, first one is P by HF.
First one is
P by HF.
P by HF, correct? Photons emitted per second is P by HF. What about the second one? First is correct. Well done. Don't get confused between what is being asked and what you are supposed to answer. The first one is absolutely correct. No doubts about it. What about the second one?
Second one also same, sir.
No. Second one cannot be same. If the second one is same, imagine what will happen on Earth, beta. Imagine A is Earth and P is Sun. Whatever energy Sun is emitting, if we get the same energy, we'll burn, beta. Cannot withstand so much of energy. Do you understand this, na? Cannot be same. And think about Neptune and Pluto, they hardly get any photon emitted by Sun. Cannot be same. I hope you are understanding the concept, yes or no?
Yes, sir.
This is known as one solar constant actually. Energy received by Earth per unit area, per unit time, solar constant. We will get to know the solar constant in probably the chapter on thermodynamics. Right now, I'm not going to tell you what is this. Okay. 2 minutes we still have. Girls, what is the answer? You had nicely prepared the theory part. What about questions? Yes? No one?
P by S. P by S, sir.
P by S. No, P by S. You are not thinking. Problem is you are just giving an answer without thinking. Number is a dimensionless quantity. P by S is not dimensionless, beta. It can never be P by S. It's dimensionless. P by S is never dimensionless. You are not thinking properly. Well, I'll give you 1 more minute, else I will do it because no one else can do it. I will have to take the burden on myself
Sir.
Yes, beta.
P by 4
P by
4 by r square s square.
P by 4 pi r square divided by
S square.
a square. I think you are going on the right direction. Probably I have missed what you had said. Let me just write it, and probably then I would be able to understand what you are saying. So, okay, let us first go on to the first part. What are the number of photons emitted? And we can straight away put the formula for this because we have already calculated this formula. This is the straight away formula we can put here. P divided by HF. What is the power emitted divided by the energy of one photon, and you will get the answer for the first one. So the first one is a pretty straightforward one, and the first one is P divided by HF. This is the first one. What are the photons received per second by A? Now, to understand the photons received per second by A, you have to find out what is the intensity at A. What is the intensity at A? It is 4 pi r square. We understand this? P divided by 4 pi r square. Yes or no?
Yes, sir.
This is the energy. Oh, this is the energy per unit area per unit time received by it. This, yes or no? Now, if I find out this energy per unit time, this is the power received by it per unit area. So I can write it as power received per unit area. So now I can find out how much power is received in terms of how much power was delivered and how much is that power that I receive. Power that I receive is P into A divided by 4 pi r square. Do we understand how I got this? The power it is emitting is P, but what I am getting here is P divided by 4 pi r square multiplied by A. Do we understand this? Now I can find out the number of photons emitted per second. Same formula. Now I have to use the received power. So the answer is PA divided by 4 pi r square HF. That is the number of photons that I receive. Do we understand this? Yes or no?
Yes, sir.
Okay. That is what you have to understand. If you can understand this, nothing like it. I'll give you 1 minute to note it down. If you have any problems, please ask.
Completed, sir.
Then comes, everyone has noted this down?
Yes, sir.
Then comes this question, sir. An electron and a photon have the same wavelength. If P is the momentum of the electron and lambda is and E is the energy of the photon, what is the magnitude of P by E? Now, here we have talked about the momentum of a photon. Right? Now we can extend this concept. Let me just add it here. See, if I go back, the momentum of a photon is E by C. Yes or no?
Yes, sir.
Okay. Now I can write this equations in a different way. I can write the lambda of photon as h by p. Yes or no? Yes or no?
Yes, sir.
The lambda of this photon as can be written as h by p. P is a momentum. Now this lambda is actually for a photon, but I can also find this lambda for any other particle because we are dealing with particles. So for any other particle also, we can find out this lambda for any other particle by dividing h by p, where p is the momentum of this particle. You know what this lambda for a particle is known as? If I find this lambda for a particle, electron is a particle, proton is a particle, neutron is a particle, helium nucleus is a particle, I am a particle, bus is a particle. I can find out this lambda for any particle. Here I found out for lambda for a photon. I can find lambda for a particle. This lambda for a particle is also known as de Broglie wavelength. Have you heard about this term, de Broglie wavelength?
Yes, sir.
So you can find out this lambda for any moving particle. De Broglie wavelength it is known as. Lambda is wavelength, and such, since it has a wavelength, since every particle have a wavelength, this is also known as matter waves. So I will probably take this small topic of matter waves just after I finish this, but I can just tell you this is my matter waves. When someone found out, when we found out that light has dual nature, light is a particle as well as a wave, depending on which case. And someone thought, okay, what about every particle also having a wave nature? And then we found out this matter waves. Any particle which has a momentum, it also has a wavelength. And you can call that particle or the wave that that particle creates as matter wave. And the wavelength of that particle is known as the de Broglie wavelength. Do we understand this? This is what you need to know about matter waves and de Broglie wavelength. That brings us back to this question. And now you should be able to solve this question. Let us see. How will you solve this question? Remember, photon is a particle, electron is a particle, proton is a particle, neutron is a particle. So what we have calculated for a photon is also applicable for a neutron or an electron or a proton or for me or for you or for anyone else. 2 minutes you have to solve this. Remember, these types of questions are in fashion these days. When I say these are in fashion, that means they are coming these days. That is why we are doing them. Whatever I do is for a specific reason that I do it. Everything that I've told you is for a specific reason that I've told you that. Can anyone? Yes, beta. You got an answer, I think. Which option?
Sir.
Option B.
Yes, sir.
Option B is absolutely correct, beta. Well done. How did we get this? Just understand the concept correctly. Everything becomes easy. An electron and a photon has the same wavelength. So, electron and the photon has the same wavelength. So, lambda is same. For electron, the lambda will be h by p, where p is the momentum of the electron. Yes or no?
Yes, sir.
Okay. For your photon, energy is given. So energy is sc by lambda for the photon. So from here I can find out the lambda hc by E. Now this is a matter wave called lambda, and this is the photon called lambda, and these both lambdas are same. That means h by p is equal to hc by E. Tung tung. What we have to calculate? Ratio of magnitude of P by E. I was calculating E by P. P by E becomes 1 by C. And that is the answer, my dear friends. Do we understand this? Yes or no? No or yes?
Yes, sir.
Ah?
Yes, sir.
Yes, sir. Then, sir, this, sir, question, sir. Will you be able to do this or not? I don't think you will be able to do this because I have not told you something. Okay. Okay, you can't do this. So probably in the next class, I'll tell you. I'll tell you matter waves, and then probably we will move ahead for this type of questions. Okay. You can do this one though. An electron has the same momentum as that of a photon of wavelength 5400 Armstrong units. What is the velocity of the electron in meter per second? So I'll give this question as a homework. In the next class, what I will do is I will just take 5-10 minutes more, and I will tell you more things about this de Broglie wavelength, because I think I'm seeing a lot of problems, and as you can see, this problem, the problem that I wanted to give you actually came in one of the IITs, so came in one of the previous exams. What I'll do is I will take some 5-10 minutes more to explain this concept of de Broglie wavelength and matter waves, and then we will move on to this photoelectric effect. It does not change anything, because in any case you know the concept of momentum, so we will just do that and then we will move ahead. Okay, so we'll do that in the next class. So we'll be covering one more topic.
Sir,
Yes, beta.
is there class tomorrow?
Oh, I mean, whenever is that? Tomorrow means whenever there is the next class. Sunday, yes, I think you should be having a class on thermodynamics. We are doing thermodynamics there in that class. Yes or no? I think there should be a class. I think so.
Timing, sir.
Timing is 9 to 12, I think. That is the normal timing. That would be the time, probably. Okay.
Bye, sir.
Okay. Then we will move ahead with this in the next class, which is on Monday. Tomorrow's class, we will be taking care of thermodynamics. Take care. If any doubts, please ask.